want to look at in this chapter is modeling internal combustion engines. There are two models that we use, the spark ignition engine. So we have the Otto cycle, which is for spark ignition engines. And this is what we typically have in our cars and light-duty trucks. It uses gasoline, there's a spark plug, it has all that sort of stuff happen, which we'll go into briefly. And then we have a diesel cycle, which is compression ignition. And in the compression ignition engine, what happens is you compress the air so the temperature is high enough that when you squirt diesel oil into it, it automatically burns. And so those are the two types of engines that we'll look at. And a little bit different than the way the text starts off, which starts off directly with the air standard Otto cycle, I wanted to look at how an actual cycle works and then what we do to model that cycle. So if I look at an engine and we look at figure 13.1 or 13.2, maybe a better drawing than what I do, as I always disclaim. So I have an intake valve, exhaust. We're going to have something that is a spark plug or a diesel injector. We'll have the piston here. It will go down and then eventually go down to the crankshaft. And this is the bore, the diameter, and it's going to operate up and down, and we call this the stroke. So basically the piston moves up and down, and through mechanisms it turns the crankshaft that goes eventually to the wheels and the car goes. And so what we want to do is model what happens to the substance in here creating the power. So let's look at that. So if I look at a PV diagram, and we'll go from, we'll have here top dead center, bottom dead center. So the piston moves between top and bottom dead center, and we'll have something like this. And so here's the compression stroke. We're going to have combustion, so the spark plug ignites, the gas mixture or the compression ignition is the stuff is squirted in, the pressure builds, and it expands down here. So we have, this is the power stroke. We have the power stroke, and now we have to exhaust it, so we're going to have the exhaust. So the exhaust, and then you're going to have intake. And then we'll have intake. So what happens is I'm compressing it. So if it's a spark ignition engine, it'll have air fuel in there. If it's a diesel engine, it'll have air in there. I'm compressing it to near top dead center. The spark goes off or ignition occurs. We then have the power stroke. The combustion builds up the temperature and pressure. Then it stops. Then the piston expands down to bottom. The exhaust valve's open. Then you push the exhaust out, and then you pull the intake in. And so if we look at these two works, this is W1, W2. And so W1 is a positive work, W2 is work I have to do to push the exhaust out and pull the intake in. So W1 is positive, W2 is negative, and W1 minus W2 is the net work that I get out per cycle. So this is what the actual engine looks like. There's slight variation depending on whether it's spark ignition or compression ignition, but basically this is what it looks like. And now, since this is what it looks like, how do we create a model for this? So this is if I had a pressure pickup. So if I had a pressure pickup in here, I could measure a diagram and get a PV diagram that would look something like this. So this is the work that the gas indicates it did. And so now, how can I model this? And I want to model things so I can vary factors and see what factors affect performance the most. And with that, we come up with air standard cycles. And with air standard cycles, we're going to have the Otto cycle as the first one, which models the spark ignition, as we had said. And in this case, the air replaces the air-fuel mixture. We're going to have heat in for combustion. We're going to have heat out for exhaust. And we're going to have reversible adiabatic or isentropic expansion and compression. And so with that, we're going to have Q in at V equals C. And we're going to have Q out at V equals C. And we'll look at, I'll draw the PV diagram so we can see what it looks like here. And so we have the PV diagram for the air standard cycle. And I can imagine I have a piston cylinder here. And it contains air. So if I start here and we have my bottom dead center, top dead center. We're going to start at bottom dead center and we have isentropic compression. So I have isentropic compression, S equals C. We're going to, from 1 to 2. And then we're going to have heat in at constant volume, so we're going to add heat. And it's going to increase the temperature and pressure. So we're going to increase it to state 3. And this is where I have Q in. Now remember, it's air in here. It's not air fuel. So now I've increased the temperature and pressure. And I'm going to have expansion, reversible adiabatic expansion from 3 to 4. And then from 4 to 1, I'm going to have heat out. So I have this diagram replacing this diagram. And with this, we'll analyze this and see what's involved. And if I look at a TS diagram, which we look at sometimes, we have isentropic compression from 1 to 2, constant volume from 2 to 3, isentropic from 3 to 4, and constant volume from 4 to 1. And the advantage here is obviously the area under the curve from 2 to 3 is the heat in, the area from the curve from 4 to 1 is the heat out, and this is the network, so we can see that directly. This is the network as well here, but I find it easier to see. Now, one of the things that characterizes internal combustion engines is their compression ratio. So the compression ratio R is equal to the volume at BDC divided by the volume at TDC. So in our case, it's V1 over V2. So very often you know about a compression ratio on a car. They say the compression ratio is 9, 10, 7, whatever, one of those things. If I look at the heat in and the heat out, Q in is equal to U3 minus U2 is equal to M C sub V T3 minus T2, and Q out is equal to U1 minus U4 is equal to M C sub V T1 minus T4. And I know that W net is equal to the sum Q. And we have a symmetric cycle. So in the text, it goes through the development of this. But basically, it's a symmetric cycle. And by that, I have the heat in and the heat out are both at the same condition. I have isentropic expansion and compression. So I have parallel symmetric things, and that allows some simplifications. And with those simplifications, so allows simplifications and the text goes through the analysis. But you can read, we'll come up with that the thermal efficiency is equal to W net over Q in, and for the Otto cycle, it's 1 minus 1 over R to the K minus 1. So we have a very simple form for the thermal efficiency for an Otto cycle.